In this session, let us discuss about the principal stresses. We have already learned that the stresses are defined within the material on a particular plane. A plane is inevitable to define a stress. As we can define infinite number of planes within a material, now the question is, what is the maximum value of stress that can be developed within a material? Obviously, this maximum value of the stress is the one which is going to make the specimen or make the component fail. So we should know what should be the value, or we are interested to find out the maximum value. And this particular maximum value is going to act on some particular plane. So this session is completely limited to analyze or to find out the maximum value of stresses. So moving forward, what exactly is a principal stress? So a principal stress is the one which is acting on a principal plane. In simple words, we can define it like this. Principal stresses are the maximum or minimal normal stresses acting on the principal planes. Now the question is, what are principal planes? Answer is right over here. Principal planes are the planes where the shear stresses are zero. Now let us see how this is going to work. See, we have defined different planes within a material, or we can define different planes in a material. In some planes, the shear stress value is going to be zero. We know that this is the equation that we have used to find out the shear stress acting on a plane which is inclined at an angle of theta. So there are planes where we have the shear stress value as zeros. Such planes are generally called as principal planes. So the normal stresses acting on that principal planes are called as the principal stresses. Now, this is a very general way of defining a principal stress, but to be very simple, in very simple words, we can say that principal stresses are the normal stresses acting on on the principal plane. There is no need to define the shear stress on this particular plane right now. Anyway, we have two different methods to find out the principal stresses. Let us go and see what are those two methods. So to find out the maximum or the maxima and minima, what we are going to do is we are going to differentiate the transformation, two-dimensional transformation equation with respect to theta. Why? Because at some particular value of plane, and that plane is very important to define the principal stress. So we are interested to find out the plane first, then we will define the stress. So we are going to differentiate this transformation equation of sigma x with respect to theta and equating it to 0 to find out the maxima or minima. That is a simple mathematics that we have done in many of the engineering mathematics topics to find out the maxima and minima. So after differentiating, you are equating it to 0. So when you differentiate this and equating it to 0, you are going to end up with tan 2 theta p equal to 2 tau xy divided by sigma x minus sigma y. You take this to the right hand side and divide sin theta by cos theta, you are going to get tan 2 theta, and you are going to get the answer as 2 tau xy divided by sigma x minus sigma y. This is one way of finding the principal plane, because the value of this particular theta is the angle at which we can locate the principal plane. Or the other method is to equate the shear stress equation to 0. That is also another method. We have already defined the shear stress, or we have already derived the equation as sigma x minus sigma y by 2 into sin 2 theta upon the sin negative plus tau xy cos 2 theta. If you equate this to 0, then also you are going to get the same answer as tan 2 theta p equal to 2 tau xy divided by sigma x minus sigma y. So in the coming slides, I will again define, I will again show, I will prove that the shear stresses on the principal planes are 0. So before that, I have directly taken it. Anyway, in the coming slides, I will show you why it is why the principal stresses are 0, or the shear stresses are 0 in a principal plane. So theta p is the plane at which we are having our principal stress. Now what we are going to do is, principal stresses are acting on some particular plane. That means it is independent of the value of theta. It should be independent of the value of theta. So this is the general equation to find out the stresses in any plane. Any plane means principal plane will also come into that condition. Any plane, you can define the, or you can find the stresses in any plane means principal stress is also acting on a particular plane. So that can also be, that normal stress can also be found using the same transformation equation. Very simple logic. What we are going to do is, we are going to replace this cos 2 theta and sin 2 theta using this particular expression. Let us see how we are going to achieve that. So if you define a triangle, right angle triangle, and if you define this angle as 2 theta p, then tan 2 theta p is nothing but opposite by adjacent. So the opposite value is going to be tau xy, and the adjacent value is going to be sigma x minus sigma y by 2. If this is the opposite and adjacent value, we all know how to define the resultant or the hypotenuse. So the hypotenuse value r will be nothing but root of sigma x minus sigma y by 2 the whole square plus tau xy square. This is a very simple mathematics. There is nothing big in this. And as I told you that we are supposed to substitute for cos 2 theta and sin 2 theta, we will find out the value of cos 2 theta p and sin 2 theta p using this triangle. So the value is nothing but adjacent by hypotenuse, and this is going to be sin theta is going 2 theta is going to be opposite by hypotenuse. So after obtaining this cos 2 theta p and sin 2 theta p, these two substitute values, you substitute these two values in our initial equation, this equation, and when you group everything together, you can eliminate the value of theta, and you will end up with a value of sigma 1 equal to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 the all square plus tau xy square. This is the equation or the maximum principal stress. So we can say that this is the equation for the maximum principal stress. Now the question is, what is the minimum value? If there is a maximum value, there has to be a minimum value. I hope you all remember the condition that we have discussed in the previous session, that the net sum of the stresses acting on any cuboidal element is independent of the orientation. That means if you add the two principal stresses together, maximum principal stress and the minimum principal stress together, then it has to be equal to sigma x plus sigma y. That's a general rule. So using this relation, you can find out the value of sigma 2. Sigma 2 is the minimum principal stress, and the value you are going to obtain is sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 the whole square plus tau xy square. It's a very simple mathematics. There is no differential terms or anything like that. So you can easily substitute it, group it, and you can obtain the value. Now when you combine these two equations, we can write the general equation for the principal stress as sigma 1 comma 2. Means if you put the suffix as 1, it is the major principal stress. If you put the suffix as 2, it is the minor, or otherwise it can be called as the maximum or minimum. So sigma 1 comma 2 is given over here, separated by a plus or minus sign. That means if it is major, the sign has to be plus. If it is minor, it has to be negative. This is how we arrived at. Now if you look at this particular equation, we can say that in this equation doesn't have any theta term. That means whatever might be the load acting on the material, irrespective of the plane, you can easily find out the principal stress. That is not going to change for that particular loading condition. Principal stress is depending only upon the normal stresses and shear stresses acting on the material. But here in this equation you have theta. This is a general expression to find out the stresses, normal stresses acting on any plane. But here there is no such term here. We can directly obtain the value of maximum and minimum principal stress. And now let us prove the shear stress acting in the principal plane is 0. Let us prove that. How we can prove it? That's also very simple. See, in order to find out the shear stress acting on the principal plane, you substitute for sine 2 theta and cos 2 theta. If you substitute this sine 2 theta and cos 2 theta, if you substitute from here to here to this equation, you can easily find the value, all these things. Okay, so when you substitute it here, what is going to be? These two terms is going to get cancelled out and you are going to get the value as 0. If you substitute it here, sigma x minus sigma y divided by 2r to here and here, when you substitute it, you are going to get these two terms will get cancelled out and the answer is going to be 0. That is how you can easily prove the shear stress acting on the principal plane are 0. So I have already combined everything in the first definition itself. The maximum and minimum normal stress acting on a plane with 0 shear stress. That 0 shear stress planes are called as the principal planes. So this is a common or general expression in which you can club everything into one single statement. So the proof is also very simple. Now the question is, we have found the maximum normal stress because sigma 1 and 2 are nothing but the normal stresses. Now there should be a maximum value of shear stress. So just do the same procedure. We already have the equation, this equation. How will you find? You simply differentiate this equation with respect to theta and equate it to 0. Same thing. You differentiated this equation with respect to theta and equated it to 0. There you are going to get the value of tan 2 theta as sigma x minus sigma y by 2 into tau xy. So in the similar manner, what we can do, we can define the triangle. We can find out cos 2 theta s and sin 2 theta s, and we will substitute these two values in the general expression, this general expression, and you are going to get the value of tau max equal to root of sigma x minus sigma y by 2 the whole square plus tau xy square. That is also a very simple equation, because if you have noticed, you might have understood why it is so simple, because this term is already present in your principal stress equation. You might have noted that. See, if you look here, you can see this particular term, that is the maximum shear time. So that is already available, and that is the value of maximum shear stresses. Obviously the minimum shear stress is nothing but negative of tau max. How? That is the next question we have to answer. So this derivation is very simple. You just follow the procedure that we have adopted to find out the principal stresses, normal principal stresses, and that is same, or that method is applicable for the shear stress also. Now if you look at this tan 2 theta s, that is nothing but sigma x minus sigma y by 2 tau xy. So if you take this, we can conclude that if you plot the tan x and tan 2x curve, we can say that 2 theta s will have two values between 0 to 360, which will be differing by 180 degree, and if you take the tan x curve, theta s will be having two values between 0 and 180, which is separated by 90 degree. That means maximum shear planes are also separated by, or mutually perpendicular, or they are separated by 90 degrees, and both will be, one will be the negative reciprocal, means maximum positive and max negative shear stress are differ only by sign. There is no change in the magnitude, but principal stresses will change by magnitude, shear will not change by magnitude. The maximum value and the minimum value will be same. I hope you all remember the principle of closed shear, everything we have discussed. Okay, now if you move forward, or if you derive the relationship between the maximum principal stress and the shear stress, maximum shear stress, It is easy because if you look these two equations, and if you subtract sigma 1 minus sigma 2, what will happen? These two terms will get cancelled out and these two will be added up together, right? You simply add this equation plus this equation. So what will happen? Sigma x plus sigma y by 2 plus root of so and so minus sigma x plus sigma y by 2 minus or minus, it is going to be plus into root of something. So these two roots is going to double up. So 2 into root of will be equal to sigma 1 minus sigma 2, and we know that root of this value is nothing but tau max. So we can say that sigma 1 minus sigma 2 is nothing but 2 tau max. So tau max is going to be sigma 1 minus sigma 2 by 2. It's very simple. See here, you subtract these two, you are going to get it like this. So this is nothing but tau max. So sigma 1 minus sigma 2 divided by 2 is also tau max. So this is an alternative method. That is a relationship between, that is how we relate the principal stresses and the maximum shear stress. It's a very simple derivation. So all these things can be easily calculated. Okay. Or the other relation that we can find is the normal stresses acting on a plane with the maximum shear stress. That is a very important thing. See, we have already proved that the shear stress acting on the principal planes are 0. But please don't think the vice versa is also true. That means the shear stress, the normal stress acting on the shear stress planes are not 0. Please don't conclude like that. Okay, there are normal stresses acting on the maximum shear planes, but there is no shear acting on the principal planes. So now the question is, what is the value of normal stress acting on the plane with maximum shear stress? The answer is very simple. You can easily find it out. How? If you think, and if you think for a second before you proceed to watch this video, you think how we can find out the value of normal stresses acting on the plane on maximum shear planes. It's very simple. Hope some of you might have got the answer right now. How you will get? You substitute the value of this cos 2 theta and sin 2 theta s, where on our general expression, this expression, and when you solve everything, this term and this term is going to get cancelled out, and finally it will end up with this particular term, and that is the value of the maximum normal stress acting on the maximum shear stress. So don't confuse everything. It's very simple. You study it in a very structured manner, then you will understand. Now let us define, or let us relate the principal planes and the maximum shear planes. If you look at this tan 2 theta s and this tan 2 theta p, they are just nothing but the negative reciprocals. Okay, so they are the negative reciprocals. It is given over here. Tan 2 theta s is this value, and tan 2 theta p is nothing but this value. This is the one is the negative reciprocal of the other. So tan 2 theta s can also be written as 1 minus tan 2 theta p. And simple trigonometric relations we are going to do, substitutions. This is going to be minus cot 2 theta. So minus cot 2 theta p can be written as tan 2 theta s plus, or tan 2 theta s plus cos 2 theta. If you take it to the other side, you can write it like this. And tan 2 theta s is nothing but sin 2 theta by cos 2. This is very basic mathematics. It's very easy for you to understand. And if you cross multiply this and if you equate it to 0, sin a cos b plus cos a sin b equal, sin a sin b plus cos a cos b is equal to 0. That is the expression for cos a minus b. So when you are going to get this as 0, cos 0 is 1 and cos 90 is 0. Again, simple mathematics. So when you equate this to 90 degree, we can say that theta s minus theta p is nothing but plus or minus 45 degree. That means theta s is equal to theta p plus or minus 45 degree. That means in very simple words we can say, if you need to find out the principal planes only. If you know the value of principal plane theta p1, you add a 90 with theta p1, it will gives you the value of theta p2. If you have the value of theta p1 and theta p2, you add a 45 with these two, you will get the value of theta s1 and theta s2. So things are getting very simple. Okay, I will go through all the details I have given right now once again, just for as a revision. See, we know we have already learned the equations to find out the normal stresses and the shear stress acting on any plane. In order to find out the value of principal stresses, we are going to equate the transformation equation, differentiate the transformation equation with respect to theta, and we will equate to 0. By using that, we will define a tan 2 theta p. From the triangle, we will find the value of cos 2 theta and sin 2 theta, and we will substitute it on this equation. And upon solving, we will get the equation for the principal stresses. Now, the same method we will adopt for the maximum shear stress. We will equate, or we will differentiate this particular expression with respect to theta, and we will equate to 0. We will get the value of tan 2 theta p, theta s. And using this relation, we will define sin theta s, 2 theta s, and cos 2 theta s. Again, we will substitute back in the general equation, and we will get the value of tau max, tau minimum. And by using the same substitution here, you will get the normal stresses acting on the shear plane. And also we have defined the relationship between the normal stress and the maximum shear stress. We have also derived the relationship between the principal planes and the maximum shear planes. So in order to understand all these things, you take a paper, and with simple mathematics you try to solve this once. So it's very simple, there is no complication in it. Okay, so these are the maximum value of normal stresses and shear stress that can generate within a material. So that's how we will identify the principal stresses and the maximum shear stress and the corresponding planes. So kindly listen to this lecture one or two times, take a paper and try to solve this. You can easily understand everything. Thank you.